Yeah.
So I thank the organizers for giving me an opportunity to talk in this conference in memory of Vasu. So today my talk has two parts. In the first part, I will talk about finite element analysis of a non-self and elliptic problem. I would like to emphasize the charge argument to deal with the error analysis for this kind of problems. And also I'll discuss the twisted charge argument, which we proposed some time ago. And in the second part, I'm going to talk on this finite element method for the non-local elliptic problem. So I'd like to share my little but very fruitful interaction with Vasu on these models. So Vasu and I was visiting IITB in 2012 for a workshop. So Vasu gave a talk on validation of these non-local models of Carrier and Kirchhoff. So where he emphasized that Kirchhoff model is more useful for certain problems. So a tribute to Vasu, we pray his soul rest in peace. So today my talk is outlined as follows. First, I talk about non-self-adjoint elliptic problem. And as I said, I will going to emphasize the charge argument and a twisted charge argument. And then I'll move on to non-local elliptic problem. Oops. So we consider the first non-self-adjoint problem. So omega is a domain. Maybe this is a two-dimensional, three-dimensional, and the model problem is written as follows. So it has a diffusion part with the A is a diffusion coefficient under some assumptions. And then there is a convective part, and then there is a reaction part. So these are the standard assumptions are assumed usually for proving the existence and uniqueness of a solution for this kind of problem. So even one can work with the A's in L infinity, but you see that we require in W1 infinity. And B and C are L infinity functions, so they're bounded. And A's, so the problem is elliptic, so assume that A is bounded below by a constant uniformly in the domain, and C is non-negative. And the force function is the L2 function. Okay, it is proved that under this assumption, there is a unique solution U for the in a weak solution H10 satisfying the variational formulation. A of U V equal to F of V for all V is H10. So they are defined in the bottom here. So you can see that, so we do usually multiply the test function and do the integration by parts. So we get this variational form. So an observation one has to make here is that we are not making any structural assumptions on the coefficients. So usually if you look at the literature, diffusion, convection, reaction equations, when the convection is dominated, there is some assumptions on the coefficients C and B to make sure that there is a unique solution. But here we are not assuming any such a structural assumption. So in that case, what we end up is like, we don't get the coercivity, but a Gaudian type inequality. So there is usually, if there is a coercivity, there is no this second term C2 minus C2, the L2 norm of V. So this norm is L2 norm. So L2 norm of the gradient minus L2 norm of the function. And there are two different constants. If the C2 is negative, then we have coercivity, and then it is the standard thing. But here the problem is we don't know about much information about C2. C2 can be positive. In that case, we don't have full coercivity. And the boundedness is as usual from the assumptions and the coefficients are bounded. So it is studied, for example, one can look at Gilbert and Trudinger book that this problem has a unique solution. And it comes from the arguments of maximum principles. So if you assume that the domain omega is say convex polygon or certain smoothness, then the solution has H2 regularity and it satisfies the following the stability. In this case, the data is only F on the right side. We don't have boundary conditions. So the C may depend on the coefficients. Okay, so and then it controlled by F. So this is the standard regularity assumption when we assume that domain is convex. So it is proved that under these conditions. And for such argument, we need also an adjoint problem that, so from the assumptions that we have stated before, the adjoint problem stated below has also a unique solution in H10. You see that because this is a symmetric part and the reaction term is also a symmetric part, but the problem is the convection term. So there is a sign change here and then divergence acting on the B into phi. So this is the adjoint of the versional problem. So you see that there is a derivative on B hidden in the equation. So this has a unique solution with the same assumption that you stated before. But if you want to have the regularity on the adjoint state, so adjoint solution, so we need that B is in W1 infinity, then phi is in H2, and this estimate is. So the weak formulation for the adjoint equation is the standard, like multiply with the test function and then do that integration by it. So we get this. So this is adjoint problem. So now let us look at the finite element approximation of the original the problem that we considered. So let tau h be a triangulation of omega. So assume that here omega is a convex polyhedral in dimension is 2 or 3. So that we can triangulate the domain omega with the triangles, so without introducing any nonconformity near the boundary, and introduce this the lowest order finite element space, which is set of all functions in H10. Basically, they are continuous and across the domain and vanishing on the boundary. And then piecewise in each triangle, when you make the triangulation, so on each triangle, when we restrict this function, it is going to be linear polynomial. So when we have this linear polynomial, the nature of the function is linear polynomial on each triangle, it has the following approximation properties. You can see that in L2 norm, the approximation is of order 2, and in the H1 norm, it is of order 1. So because we are using linear, if you use higher order, it will change. And also we need more regularity and function B. So the finite element method is to find UH such that it is mimicking the continuous problem, replace U by UH and then test with only the discrete functions VH. Okay, so as I said, the existence of the solution for continuous problem was done using some maximum principles. So if you have to do the existence and uniqueness of solution for this, so we have to rely on the maximum principles. But for discrete problems like this, the maximum principles are not that easy. We need to assume something on the mesh. So there is a different argument due to Charles, which I'm going to show. So to show that existence and uniqueness of solution UH, because it's a finite dimensional problem, because VH is finite dimensional, so it is equivalent showing that if you take F is 0, because it's linear, and then show that UH is 0. So that gives the uniqueness, and which implies there is a unique existence of the solution. So this is what Charles proves. So assume that the adjoint problem has H2 regularity. Okay, I made it simpler assuming H2, but it is we can assume what H1 plus delta positive. That is fine. So then the discrete problem has a unique solution. So how the argument goes is, so assume that for homogeneous problem, we have to show that 0 is a solution. So assume that F is 0. And then UH is going to satisfy this. We need to show UH is 0. But if it is a problem is coercive, then we would have got from the coercivity UH is 0. But the problem is not satisfying the coercivity, so we have this, it is a satisfying a guarding type inequality. So the gradient of UH is bounded by constant term times the L2 norm of UH. So we can't conclude anything from here about the UH showing that UH is 0. So then use the ab initio duality argument. So for that, we bring the adjoint equation here. So adjoint problem was looking for a solution phi satisfying some equation with given some right hand side. Here pick right hand side, this one to be UH. Because this is finite dimensional problem, there is always a solution. The thing is to show that uniqueness, right? So UH, if you take UH and then construct this adjoint problem at continuous level. Okay. Then what we can see that if this is the adjoint problem, then I take V to be UH as to start, then I get L2 norm here. then this will be A of UH comma phi. I'm taking V to be UH. Then, but A of UH V is 0. So all this, if I use this kind of orthogonality, I can subtract some function V here. Now this V can be any arbitrary because it is 0 for any V. And I apply the boundedness of A, we get this gradient of UH and the gradient of phi minus V. So now I can use approximation properties of this the space VH, and phi is satisfying a second order equation. So we expect that it is H2, and under our assumptions that phi is in H2. So we can use the H2 regularity and use approximation property to get one H here. Okay. But then adjoint problem has the stability. The L2 norm, the H2 norm of phi is bounded by the L2 norm of UH. If I use that, I get this. So there is a square here, and there is L2 norm of UH. I can cancel one term to get that L2 norm is bounded by C times H into gradient of UH. So I have two inequalities. The gradient is bounded by the UH, and then UH is bounded. L2 norm of UH is bounded by the H times gradient of UH. So if I combine this, I get the gradient of UH is bounded by CH into gradient of UH. Okay. So, but H is our mesh, the mesh size in our triangulation. I can make, if I take a finer triangulation, making H small, I can make this CH is less than 1. So I get a contradiction that UH must be 0. If I started with UH is not 0, I get this. Or I can make it that push this back and then get UH is 0. So this holds for small mesh sizes H. So this was the short argument. So it uses the regularity of the adjoint problem. So what if there is no regularity, that you are assuming that for adjoint problem, regularity of the adjoint problem requires the smoothness of the convective term B. So if B is only L infinity, how can we do the analysis for this problem as the question. So first what we did is that, so there is a unique solution for this discrete problem. So first let us show that there is a unique solution for this discrete problem, looking for phi h satisfying this equation for any given UH. Okay. So this force is given to be any UH, and then look for a discrete function phi h satisfying this discrete problem. If I can show that this problem has a unique solution, essentially I'm showing that the A transpose, the original discrete problem gives that AX equal to B. The A is the matrix, stiffness matrix. In this case, I'm having that A transpose into something. So I'm showing that A transpose is invertible, essentially that. So how do we show uniqueness of this solution of this problem? So we again use the guarding type inequality and take V is the phi h. So I have this gradient and then minus C2 times L2 naught, which is phi h into phi h. But this phi h is satisfying this, I get this. So applying the Cauchy-Schwarz inequality, here I get L2 norm, and there will be an L2 norm, and this L2 norm together will be combined, and then, so if you remove the squares, we get this. Okay, so there is again the L2 norm as in the previous case, but Schwarz did. So we need to push it back. So instead of now using so we were actually looking for a discrete adjoint problem. So what we use the same ab initio duality argument for discrete problem, the discrete adjoint problem. So we construct a dual problem for this dual problem. So W is a solution of this equation. So given any phi h, so there is a solution, unique solution W satisfying this equation for all V's in H10. This comes from again from the existence theory for the initially we started. So given any right hand side, there is a unique solution always. So I change the right hand side here and then looking for a W. So now if I take V is phi h, then so here then it will be FW phi h, which is this, but now I have to use that phi h is satisfying this equation. So I subtract something here, and then because this V has to be discrete function, so I subtracted a discrete function and then use any equation, I get QHWH. Then use the Cauchy-Schwarz inequality and then approximation property for W, because W again satisfying a second order problem. So there is an approximation coming from this this term, so that H is coming, and then there is a gradient, and then this L2 norm is scattered here. So again, this is using the elliptic regularity. H2 norm is controlled by the L2 norm of phi h. So we have this term, but I have this gain H here. Okay, so therefore what we have come after cancellation of one term, so the L2 norm of phi h is bounded by this. Now if I substitute this L2 estimate for the L2 norm of phi h in this, so I get this one. Okay, so from the above two equations, if I make h small, so I can this again push back and get this estimate. The gradient of phi h is controlled by the L2 norm of phi h. So this is the stability estimate for a discrete dual problem. Okay, so from here also the existence of a unique solution of phi h follows, because it's a linear problem. If you make UH is 0, we have to show phi h is 0. So this estimate implies that we put UH is 0, we get phi h is 0 because of Poincare inequality. So this shows the existence of a unique solution for this discrete dual problem. So here we didn't use in this, we used the actually the regularity of the original problem, but not the adjoint problem. So now to show that the existence of a unique solution for the original discrete problem, what again, if you take f is 0, then we need to show US is 0. So suppose that UH is satisfying this equation, A of UH V is 0 for all V in VH. So then I can take in this equation V is UH. So UH square is A of UH VH. But this is again a discrete function. So this will be 0. We have UH is 0. So the discrete problem has a unique solution. So we avoided the regularity of the adjoint problem. The similar way, the way that we did the discrete adjoint problem, using that same problem, we can derive the following error estimates. So the energy estimate comes as quasi-optimal, that the error in the energy norm is up to the best, up to a constant, it is the best approximation. Okay, but if you want to gain some additional order of convergence for L2 norm, of course, we need to use again the regularity of the H2, the adjoint H2 regularity of the adjoint problem. So with that, we assume we get again optimal. But so with this twisted argument, what I want to highlight is that the twisted charge argument without adjoint, the regularity of the adjoint problem, we get this energy norm error estimate. So this was actually this work was done in my thesis long time ago for showing the existence of a solution for the adjoint inconsistent method. So those were, that time it was the DG methods were so popular. There was this non-symmetric penalty, interior penalty Galerkin method. So we don't have a sharp L2 estimate comparing to the energy estimate. So we wondered what to do. Then this idea came, and then we were successful in deriving error estimates for adjoint inconsistent methods. So, but it turned out that this idea, now we can see that it can be generalized for any, for standard conforming methods for a non-self adjoint equations, but without using the regularity for the adjoint problem. This is the first part, and the second part. So this is about it's a different problem actually. So it is consider this problem. It's a quasi-linear. It's a nonlinear elliptic problem. The nonlinear coefficient is having this, it's called as a Dirichlet energy. So there is a function that depends on the global L2 norm of the gradient of U, and then there is standard that the second order term Laplacian is f in omega. And we have, for simplicity, say homogeneous Dirichlet boundary condition. So I was looking at some literature about nonlinear problems those days. So I came across this model and then try to see how we can approximate this problem. Then it's surprising to me that it is not the standard way that we can handle this problem. So it made me to look at this problem. So this problem originally is proposed as extension of the classical stationary wave equation, but originally it was time dependent, the wave equation will be UTT, but the stationary version is this. And so it considers the effect of volume change while the vibration takes place. So that's a model proposed, and so in the literature it is known as Kirchhoff type model, a non-local problem. And also, as I mentioned, Vasu was working at those days on validating the models of these non-local problems. He said that this should be called the Kirchhoff and the Nasima model. So the paper of Vasu is quoted here. He actually validated the model of carrier and then the Kirchhoff this kind of model for the time dependent using some numerical computations, and then he came up with some conclusions that this model is better suited for more general than this carriers model. So, and it motivated to study study this kind of problem because it has very good applications in biology and physics. So let us look at how we can solve this equation numerically. So consider again a triangulation of omega and the same space that it is piecewise linear and it's globally continuous. So let us just discretize this equation in the standard way. So, and then, so it is written here that basically what we do, this is a basically m, this one is a constant. So multiply with the test function and do the integration by parts. We get this inner product, grade UH and grade VH, and then FVH. But then the nonlinear term is here. Okay, so this is the discrete problem. If you mimic the continuous problem, we get this. And okay, how do we solve this using the Newton method computationally? This is I want to show. So if take phi to be the Lagrange basis for this space, conforming entanglement space, I mean enumerate from 1 to n. So UH is UH is coming from this space, so you can write it as alpha I into phi I. So alpha i's are unknown, so we need to find alpha i's, then we find UH. So then this discrete problem is equivalent to finding this UH satisfy this, but the UH is as a function of alpha, it is this. So we express this as a nonlinear algebraic equations. Fj alpha is 0 for j is 1 to n. So this j index is when you test with a test function phi j. Okay, UH is as it is, but we replace v by phi j, you get one equation. So we have n test functions, so we'll have n equations and there will be n unknowns. Okay, so if we express UH in terms of that alpha I phi I, so we get this. Now to solve this nonlinear algebraic equations, if you use Newton's method, it is like given alpha, you start with the initial guess alpha naught, and you need to find the next iteration alpha n such that it satisfies this equation. So this is a Jacobian, inverse of the Jacobian is involved here, and it is computed as the partial derivative of fj with respect to alpha k. That is the jk component of the matrix J. So if you compute and see this, how it looks. So differentiate fj with respect to alpha k and evaluate it at the previous iteration alpha n. So it will be the first term. There are two UH here, so we differentiate here and then differentiate here. If you differentiate the first term, this one will be phi k because alpha k, and this is given. So this is a constant times this one. This is the standard stiffness matrix that we see for the local elliptic problems or the standard elliptic problems. But then we have the additional term that comes from this nonlinearity, the derivative of m evaluated at this previous iteration UH, and then this one. So you see that there is a phi k here and then integrate here, and there is another integration with the UH and then phi j. So you see that here phi j and phi k, they have usually the test functions the basis functions are formulated, the basis functions are constructed so that they have small support, and then we get the stiffness matrix sparse. That's basically the success of finite elements. You get a sparse matrices, you can go, I mean, increase the dimension so large to be able to do the computations. But if you look at here, this is not going to give a sparse matrix. Okay, so for any jk, so this combination, because of this, it is not going to be 0. So it's a Jacobian is a full matrix in this case because of this non-local term involved in the equation. So then thought that so we need to have a remedy for this. So what we proposed was that introduce another variable d in it's a constant and find UH such that it satisfies this augmented system. So we introduce one more unknown and then write this. So with this, okay, we can introduce now, I can write this in terms of nonlinear algebraic equations. So we have this from the second equation, as I said before, we replace VH by Phi, you have n equations. And then you add one more equation. This is the one. Okay, so there are n plus 1 equations and then n plus 1 unknowns. And if you apply Newton method for this, the Jacobian, if you compute the Jacobian for this, it will take the following form. It has a matrix A, n by n matrix A, and then there is a column vector B, and there is a row vector C, and then there's a constant -1. Okay. So this is n by 1, and this is 1 by n, and then there is this. So this total matrix size is n plus 1 by n plus 1. And you see that this the matrix A has components m into d, and then this is the standard stiffness matrix that we encounter for the local elliptic problems. And then other one is the vector, it's a full vector, and then this vector C is again a full vector. So this is, so there is a sparse matrix A and there is a column vector B and row vector C and -1. So how do we do computations with this kind of structure? So there is a way to do it is called the Sherman-Morrison-Woodbury formula. So what it tells that if you have to solve this matrix times xy equal to some vector t, or if you write in terms of equations, ax plus by is t and cx minus y is t. So from the first equation, we can, so A is, you can see that A is of this form, is the stiffness matrix for the local elliptic problem. This is a sparse matrix, and M is the diffusion coefficient. So the standard assumption is assume that M is positive. So the matrix A is invertible. So we can invert A and then write X in terms of the other things. So A inverse T minus A inverse of PY. This is from the first equation. So using that, first the expression for X and substitute in the second equation, we get the expression for Y, and simplifying Y, we get this form. So this is a scalar, Y is a scalar, so it is E is a scalar, and then everything is a scalar. Now once this is all known quantity, so E is given, so everything is known, so Y is known. Now from this formula we can compute Y, and then we can compute X as from the previous equation. X in this equation, we substitute Y, we get this. So there is of course you see that there is multiple times we have to inverse A, but so that this is a sparse matrix one can use, and then that correspond to the standard the elliptic problems. One can use some multi-grid techniques or some other techniques. The well-known techniques that are available to invert the stiffness matrix can be efficiently used in computing this. But there are some things like A inverse of B is multiple times used, and A inverse T is also used multiple times. So like if you compute once, you can use it multiple times. So it makes the things very easy and efficient to do the computations for this kind of non-local problems. So the analysis, we are not getting into that, but so one has to really look at to do the error analysis for this. So we need to work on some assumptions, and then one can do this. And of course, we under some conditions we have proved that this method, but we proposed is converging optimally, and so that is verified. But if you, of course, so what conditions you put on M, that depends on how better you can improve the analysis. So. But the method doesn't change, so one can do the efficient computations using the Newton method, resolving into the local elliptic problem. So the conclusions is that, so in the first part, so we have proposed a way in the absence of the regularity of the adjoint problem, the twisted charge arguments give error estimates for the non-self adjoint problem. So this is one idea that we presented. And then the other one is that if you augment the formulation for non-local elliptic problem, it gives a sparse Jacobian, and the standard solvers can be used to do the computations. And one more thing is that about non-self-adjoint problems, the error estimates, if you had seen that, are derived under the assumption that the mesh size is small to do the pushback arguments. So how small this as h should be is theoretically we proved, but computationally one has to know how small this h should be. That of course that constant times h should be made less than 1, and that constant involves many constants. For example, the data in the problem, and then the constants from the approximation theory, and then constants from Poincare inequalities. So what are the constants that we have used in the estimate? If you know some idea about those constants, then one can have an idea how small h the mesh size should be taken. Is one thing. But sometimes these constants may be overestimated, and then it could be like overestimating can lead the expensive computations. So you may have to make h very small. So recently people have been looking at proposing stabilized finite element methods for handling the smallness of mesh size. So maybe one can look at those kind of things. I think it's not well settled, but still, like for people working in finite element, this is one thing one may look at. So the following references, this was the original Shah's paper. It was very old, you see that 1974. And the first part is based on this paper. It was original, as I said, it was introduced for the handling DG methods, which are adjoint inconsistent. Now we could see that it has done something else. And then this was also studied for strongly nonlinear elliptic problem, the other paper. And this is about the second part of my talk. So these are old, but I felt it is have simple ideas I can share quickly with you. Thank you.